Breaking tonight, November 11th, 2025. Astronomers have just confirmed what could be one of the most extraordinary space events ever witnessed: the interstellar object. 3I Atlas appears to have exploded near the Sun. New telescope images reveal colossal jets of gas and debris stretching millions of kilometers across space, activity far too powerful to be explained by any known comet behavior. The numbers don't add up, the energy defies physics, and scientists are scrambling to understand whether we've just watched a natural object meet its fiery end, or witnessed something far more deliberate unfolding just beyond the Sun. Stay until the end, because in the next few days, that debris will drift into open space, and if its trajectory shifts even slightly, it could reveal whether this was a random detonation, or the opening move of something none of us is ready for. Keep watching. Breaking tonight, November 11th, 2025. Astronomers across the globe are reporting something that shouldn't be possible. An object from beyond our solar system, designated 3I Atlas, appears to have exploded near the Sun. We're not talking about a typical comet fizzling out. We're talking about jets of gas and debris stretching millions of kilometers across space. Activity so violent and energetic that it defies every model we have for how these objects should behave. This is the third confirmed interstellar visitor to enter our solar system. The first, 1I/Oumuamua, arrived in 2017 and sparked endless debate with its bizarre cigar shape and strange acceleration. The second, 2I/Borisov, showed up in 2019 and behaved exactly like a comet, which was almost disappointing in its normalcy. But 3I Atlas? This one is rewriting the rules entirely. The object was discovered on July 1st, 2025, by the Atlas Survey Telescope in Chile. Within days, astronomers realized they were looking at something extraordinary. The trajectory was hyperbolic, unbound, meaning this visitor was never going to stick around. It came from the vast darkness between stars, traveling through the Milky Way for who knows how long, possibly billions of years, before crossing paths with our Sun. Its orbit told the story of an outsider, something that belonged to no planet, no star system we could identify. For months, 3I Atlas approached the Sun, brightening as solar radiation heated its surface. Observers expected a show. They got something else entirely. On November 9th, 2025, stacked images captured between 5:08 and 5:22 Universal Time revealed what can only be described as colossal jets. One jet stretched roughly 1 million kilometers toward the Sun. The other, pointing in the opposite direction, extended up to 3 million kilometers into space. To put that in perspective, you could fit about 7 Earths end to end in the shorter jet. The longer one, that's roughly 8 times the distance from Earth to the Moon. These aren't gentle puffs of gas. These are monstrous outflows, eruptions of material racing away from the object at approximately 0.4 kilometers per second. That's 400 meters every single second, faster than the speed of sound on Earth, sustained over hours, perhaps days. Now here's where things get weird. If 3I Atlas were behaving like any normal comet, the amount of mass loss and energy output implied by those jets should not be possible. The numbers simply don't work. Let's talk about those numbers because they're staggering. The estimated mass loss rate near perihelion, the closest approach to the Sun, hit approximately 2 million kilograms per second. That's the equivalent of losing 2,000 metric tons every single second. Over recent weeks, the object appears to have shed roughly 5 billion tons, about 16% of its total estimated mass of 33 billion tons. For context, that's like losing 16% of your body weight in a month, except you're a comet made of ice and rock being cooked by the Sun. The solar flux at the object's perihelion was measured at around 700 joules per square meter per second. That sounds like a lot, and it is. But here's the problem. When you calculate the maximum surface area that could absorb that solar energy, even under ideal conditions, it's nowhere near enough to power the observed mass loss. The math fails spectacularly. To match the observed outflow, assuming the jets are powered by carbon dioxide sublimation, you'd need an absorbing surface area equivalent to a sphere roughly 23 kilometers in diameter. If you assume water ice instead, you'd need something closer to 51 kilometers across. But when Hubble Space Telescope measured 3I Atlas back in July, it found a nucleus no larger than 5.6 kilometers in diameter. The energy budget is off by an order of magnitude, maybe more. There's another problem. Early observations in August showed a mass loss rate of about 150 kilograms per second. Respectable for a comet, nothing alarming. But near perihelion, that rate exploded to 2 million kilograms per second. That's a jump of 4 orders of magnitude. The relationship between heliocentric distance and mass loss follows a power law with an exponent of roughly negative 10.5. Normal comets? They're in the range of -2 to -4. 3I Atlas is burning 10 times harder than physics says it should. And there's one more twist. The statistical likelihood of detecting an interstellar object of this size, on this trajectory, during a decade-long survey? Less than 0.1%. When you factor in its retrograde orbit, meaning it's traveling in the opposite direction of most objects in our solar system, and its near-ecliptic path, the odds drop to roughly 1 in 100 million. We shouldn't have found this object, but we did. So the question hanging over the scientific community tonight is simple and terrifying. Did we just witness a natural object meet its fiery end near the sun, torn apart by forces it couldn't withstand? Or is this something far more exotic, perhaps artificial, engineered, or deliberate? Because if 3I Atlas shattered into fragments, we may have witnessed the death of an interstellar traveler we'll never see again. But if it remained intact despite those cataclysmic jets, if it's still out there holding together against impossible odds, then something even stranger is at play, and we need to figure out what that is before it's too late. Let's dig into what the telescopes are actually showing us, because the devil is in the details, and those details are increasingly difficult to explain. The stacked images from November 9th aren't just pretty pictures. They're evidence of something fundamentally wrong with our understanding of how interstellar objects should behave. The imaging sequence captured between 5:08 and 5:22 Universal Time shows 2 principal jets dominating the scene. The geometry alone is bizarre. Most comets develop an anti-sunward tail, pushed away from the sun by solar radiation pressure and the solar wind. You get a bright coma surrounding the nucleus and a tail pointing away from the sun, sometimes 2 tails, one of dust and one of ionized gas. It's predictable, textbook behavior that's been observed thousands of times. 3I Atlas shows a massive jet pointing toward the sun. That's already unusual. Solar radiation should be pushing material away, not allowing it to fountain back toward the source of heat. The anti-sunward jet is 3 times longer, which makes more sense directionally, but the sheer scale is unprecedented. These aren't delicate streamers. These are artillery blasts of material being expelled with enough force to maintain coherence over millions of kilometers. The images were captured by Frank Niebling and Michael Buchner using deep stacking techniques, which means they combined multiple exposures to bring out faint details invisible to single snapshots. It's a standard method, but it also means we're relying on careful calibration and processing. Any errors in alignment, any artifacts from stacking, could introduce features that aren't real. But multiple independent observers have confirmed the jet structure. This isn't a processing glitch. It's real. Now let's talk about what's inside those jets. The James Webb Space Telescope observed 3I Atlas on August 25th, 2025, and the results were immediately striking. The coma, the cloud of gas surrounding the nucleus, is dominated by carbon dioxide. The carbon dioxide to water mixing ratio came in at approximately 8.0, plus or minus 1.0. That's among the highest ratios ever observed in comets. Most comets are primarily water ice, with carbon dioxide as a secondary component. 3I Atlas flips that script. The SWIFT satellite captured ultraviolet observations that detected hydroxyl emission, which serves as a proxy for water. The emission rate was measured at approximately 1.35 times 10 to the 27th molecules per second, translating to about 40 kilograms per second at a heliocentric distance of roughly 3.51 astronomical units. That's about 3.5 times Earth's distance from the sun. Even at that range, the object was already outgassing significantly, but nothing compared to what came later. Here's where the energy budget paradox becomes impossible to ignore. At perihelion, solar energy arrives at the object's surface at roughly 700 joules per square meter per second. To power the observed mass loss through sublimation, you need to absorb enough energy to vaporize ice, lift it off the surface against gravity, and accelerate it to escape velocity. The latent heat of sublimation for carbon dioxide is about 570 kilojoules per kilogram. For water ice, it's closer to 2,800 kilojoules per kilogram. When you run the numbers, assuming maximum possible absorption of solar radiation and perfect conversion of that energy into sublimation, the required surface area is absurdly large. If carbon dioxide is doing the heavy lifting, you need a sphere roughly 23 kilometers in diameter. If water ice is the primary driver, you need 51 kilometers. But Hubble measured the nucleus at no more than 5.6 kilometers across in July. The surface area simply isn't there. Something else has to be powering these jets, or our assumptions about sublimation efficiency are catastrophically wrong. The escalation in mass loss is equally baffling. In August, the object was shedding about 150 kilograms per second. Respectable, normal, exactly what you'd expect from a distant comet beginning to warm up. By perihelion, that rate had jumped to 2 million kilograms per second. That's a factor of roughly 13,000 times increase. The relationship between heliocentric distance and mass loss rate typically follows a power law. For most comets, that exponent is somewhere between -2 and -4, meaning activity increases modestly as they approach the Sun. 3I Atlas shows a power law exponent of approximately -10.5. It's not just steeper than normal, it's off the chart. There's one more piece of the puzzle that doesn't fit. The statistical probability of detecting an object like this is vanishingly small. Surveys like Atlas scan the sky night after night, cataloging everything that moves. The volume of space they can detect objects in is limited by brightness and speed. For an interstellar object as massive as 3I Atlas, with its particular trajectory and brightness, the detection probability over a decade-long survey is well below 0.1%. Factor in its retrograde orbit, moving opposite to the majority of solar system objects, and its path close to the ecliptic plane, and you're looking at odds closer to 1 in 100 million. We shouldn't have found this thing. But we did. And now that we have, it's behaving in ways that violate every expectation. The observational facts paint a picture of an object whose physics is wildly different from anything we've studied, or they suggest our interpretation, that this is just a natural comet doing comet things, is fundamentally wrong. The stage is set for two competing narratives, each as troubling as the other, and neither of them easy to swallow. We're left with two primary explanations for what happened to 3I Atlas, and neither one is particularly comforting. The first is straightforward, rooted in physics we understand, but requires accepting some extreme conditions. The second ventures into territory that makes most scientists uncomfortable, but refuses to go away because the data won't let it. Narrative 1 is the natural breakup scenario. Imagine an interstellar comet, ancient and fragile, wandering through the galaxy for billions of years. It's been exposed to cosmic rays, interstellar shocks, temperature extremes close to absolute zero. Its structure is probably not uniform. There are cracks, voids, layers of different ices, frozen at different times under different conditions. As it enters the inner solar system and approaches the Sun, thermal stress begins to build. One side heats up while the other remains frozen. The temperature gradient creates mechanical stress. Tidal forces, though weaker than those that ripped apart Shoemaker Levy 9 near Jupiter, still apply. And then there's sublimation itself. Gases trapped beneath the surface, suddenly vaporizing, creating pressure, seeking escape. At some point, the object gives way. It fractures. Maybe it breaks into a few large pieces. Maybe it shatters into dozens of smaller fragments. The key effect is an immediate increase in surface area. More surface means more area exposed to solar radiation, which means more sublimation, which means more gas, which translates into those massive jets we observed. The math on this is interesting. To explain the observed mass loss rate using sublimation alone, you'd need to increase the surface area by a factor of roughly 16, assuming the nucleus started at Hubble's measured 5.6 kilometer diameter. That would require breaking the object into at least 16 pieces, each maintaining enough integrity to sublimate effectively. It's plausible. Comets have been observed fragmenting before. Shoemaker-Levy 9 famously broke into more than 20 distinct fragments before plunging into Jupiter's atmosphere in 1994. But that was under Jupiter's immense tidal forces at extremely close range. 3I Atlas was much farther from the Sun, experiencing far weaker tidal stress. To fragment so dramatically under those conditions suggests an object that was already on the verge of coming apart, held together by little more than weak gravity and ancient ice. The pros of this narrative are clear. It explains the sudden spike in activity, the enormous jets, the apparent mass loss. It fits within known physics. We don't have to invoke anything exotic or speculative. The cons, however, are troubling. Even with fragmentation increasing surface area, the energy budget still barely closes. You're still relying on solar heating to drive everything, and the numbers remain uncomfortably tight. The timing and scale of fragmentation required is extreme, and there's no direct observation yet of multiple distinct fragments, though admittedly, resolving individual pieces at that distance is incredibly difficult. Narrative 2 is where things get speculative and, frankly, uncomfortable for mainstream science. What if the jets aren't sublimation driven? What if they're exhaust, propulsion? The idea is that 3I Atlas isn't just passively outgassing as the sun heats it, it's actively expelling material in a controlled manner, generating thrust, perhaps to alter its trajectory, or decelerate, or maneuver in some way. This would require exhaust velocities in the kilometers per second range, far higher than typical cometary outgassing at a few hundred meters per second. Higher velocities mean you need less mass to generate the same momentum, which would help explain how the object produces such massive jets without requiring an impossibly large surface area. This hypothesis leans heavily on statistical improbability. The odds of detecting an object like 3I Atlas, given its size, trajectory, and arrival time, are astronomically low. Its retrograde orbit, moving counter to the typical flow of solar system objects, is unusual, but not impossible. Its path close to the ecliptic plane, where planets orbit, is convenient for observation, but also statistically unlikely. Add it all together, and some researchers argue the probabilities suggest this isn't a random wanderer. It's something deliberately placed or directed. What signatures would we expect if this were an engineered object? Sustained acceleration beyond what sublimation could provide. Anomalous changes in orbit that can't be explained by gravitational interactions or normal non-gravitational forces. Reflective surfaces with unusual spectral properties, cyclic activity that suggests internal processes rather than purely thermal responses. So far, we don't have definitive evidence of any of these. Early reports hint at unusual acceleration patterns, but the data is still being analyzed and debated. Spectral observations show mostly what you'd expect from ices and dust, but absence of evidence isn't evidence of absence. Most scientists firmly reject the engineered hypothesis. It invokes an extraordinary claim, the existence of extraterrestrial technology in our solar system, which requires extraordinary evidence. Mainstream coverage emphasizes the natural explanation, and rightly so. The burden of proof for artificial origin is enormous, and we're nowhere near meeting it. But the hypothesis persists because the anomalies persist. The energy budget doesn't close. The statistical odds are troubling. The behavior is unlike anything we've seen before. There's a third possibility, a hybrid model. What if 3I Atlas is a natural object, but one so different from solar system comets that it behaves in ways we don't recognize? Interstellar objects come from other star systems, other formation environments. Maybe this one formed in a region exceptionally rich in ultra-volatile ices, like nitrogen or carbon monoxide, frozen at temperatures near absolute zero. When exposed to even moderate solar heating, these ices sublimate explosively. Or maybe the object was already fractured from a previous encounter, perhaps a collision in its home system billions of years ago, and the structure is so compromised that it behaves unpredictably. We have an observational checkpoint coming. On December 19th, 2025, 3i Atlas will make its closest approach to Earth. Telescopes will be watching. We need to look for separate nuclei, multiple fragments traveling in formation. We need to search for dust arcs, trails of debris that would indicate breakup. We need to measure any non-gravitational acceleration with precision, looking for anomalies that can't be explained by outgassing. We need to see if there's a persistent single nucleus, or if the object has truly shattered. And we need unusual spectral features, anything that doesn't fit the ice and rock model. If this is an engineered object, the implications for the search for extraterrestrial intelligence and astroengineering are staggering. We'd have physical evidence of technology from beyond our solar system, something we could study, track, potentially even rendezvous with if we moved fast enough. But if it's natural, if this is just an interstellar comet with properties we didn't anticipate, then it tells us the universe is full of objects we've never encountered, behaviors we've never modeled, physics we're only beginning to understand. Either way, 3i Atlas is forcing us to expand our thinking, and that expansion is just beginning. Let's talk about what we're not seeing in the headlines, the messiness beneath the surface. Because the story of 3i Atlas is more complicated and uncertain than the clean narratives suggest. Science is rarely tidy, especially when dealing with data from millions of kilometers away, captured by instruments operating at the edge of their capabilities. First, the imaging itself. Those spectacular images showing the million-kilometer jets? They came from deep stacking techniques employed by Frank Niebling and Michael Buchner. Deep stacking is a powerful tool. You take multiple exposures of the same field, align them precisely, and combine them to boost signal and reveal faint details. It's standard practice in astronomy, but it's also a process that requires careful calibration. Misalignment introduces streaks. Background subtraction errors create false features. Saturation in bright regions can bleed into surrounding areas. None of this means the jets aren't real. Multiple independent observers have confirmed the basic structure. But it does mean we need to be cautious about interpreting fine details and drawing conclusions from subtle features that might be artifacts. Another issue is distinguishing dust from gas. When we see jets in images, we're usually seeing sunlight reflected off dust particles. Gas, unless it's ionized or fluorescing under ultraviolet light, is largely invisible. The mass loss calculations depend heavily on assumptions about the dust-to-gas ratio, the size distribution of particles, and how efficiently they scatter sunlight. Change those assumptions even slightly, and the inferred mass loss rate changes dramatically. We're working with estimates, not direct measurements, and the uncertainty bands are wider than most people realize. Velocity estimates also carry significant uncertainty. The quoted outflow velocity of approximately 0.4 kilometers per second is derived from observations of jet morphology and how structures evolve over time. It's not a direct measurement of individual particle speeds. It's an inference based on modeling how jets expand and disperse. Different models give different velocities, which cascade through every subsequent calculation of momentum, thrust, and energy requirements. There are alternative natural mechanisms that rarely make it into the popular discussion. Ultravolatile ices, for instance. Nitrogen and carbon monoxide freeze at much lower temperatures than water or carbon dioxide. If 3i Atlas formed in an exceptionally cold environment, perhaps in the outer regions of another star's protoplanetary disk, it could contain significant amounts of these ultravolatiles. When exposed to even modest solar heating, they sublimate rapidly and explosively. We rarely see this in solar system comets because they didn't form in environments cold enough to preserve substantial nitrogen or carbon monoxide ice. But an interstellar object? All bets are off. Another possibility is a micro-impact cascade. 3i Atlas has been traveling through interstellar space for billions of years. It's been hit by interstellar dust particles moving at relative velocities of tens of kilometers per second. Each impact delivers enormous kinetic energy, potentially fracturing the surface, weakening the structure. When solar heating begins, those pre-existing fractures become pathways for gas to escape, and the object comes apart not because the sun destroyed it, but because it was already compromised by eons of sandblasting in the interstellar medium. Or consider internal outgassing triggered by a solar shock. Imagine the object has a thick crust, maybe meters, of non-volatile material covering volatile ices beneath. For billions of years, that crust held firm. But as the object approaches the sun, thermal expansion causes the crust to crack. Suddenly, deeper layers are exposed, and volatile rich material sublimates en masse, producing a violent outburst that looks like an explosion but is really just a delayed response to heating. Then there's the social and scientific reaction to the alien probe hypothesis. Avi Loeb, a prominent astronomer at Harvard, has been vocal about the possibility that some interstellar objects might be artificial. His arguments gained public attention with Oumuamua and have resurfaced with 3I Atlas. The hypothesis energizes the public. It generates headlines, sparks imagination, and gets people interested in space science. But it also risks sensationalism, oversimplifying complex data, and creating expectations that science can't meet. The vast majority of astronomers remain firmly in the natural object camp. The data anomalies, while real, don't yet justify invoking extraterrestrial technology. But those anomalies do keep the alternative ideas alive, hovering at the edges of respectability, refusing to be dismissed entirely. There's an ethical dimension here too. How do we communicate findings when the data is still uncertain? The word explosion is evocative, dramatic, perfect for headlines. But what does it actually mean in this context? It doesn't imply a nuclear blast or chemical detonation. It means rapid, energetic disintegration, fragmentation, catastrophic mass loss, a sudden change of state. The distinction matters. Overstating confidence in preliminary findings risks undermining public trust when interpretations change as more data arrives. Understating the significance risks missing opportunities to engage people with genuinely extraordinary discoveries. Historical analogs offer some perspective. Shoemaker Levy 9 fragmented dramatically near Jupiter, but the tidal forces there are immense, and the environment is nothing like what 3I Atlas experienced. Major sun-grazing comets like Comet Lovejoy have passed within a solar radius of the sun's surface, surviving against incredible odds, but still behaving according to expected physics. 3I Atlas, by contrast, never approached that close, yet its behavior diverges more dramatically from expectations than objects subjected to far greater stress. And then, there are the quiet speculations about secrecy and observing. Solar monitoring satellites, private observatories, classified military space surveillance systems, all of them may have captured data on 3I Atlas that hasn't been made public. This isn't necessarily sinister. Data processing takes time, calibration requires care, and not every observation is immediately shared with the broader community. But it does mean the full picture might not yet be visible. There could be observations showing fragmentation events we haven't seen, spectral, features that haven't been discussed, trajectory changes that haven't been reported. The uncertainty is itself part of the intrigue. What does seem clear is that the messiness of the data, the uncertainty in interpretation, the competing hypotheses, all of it reflects the reality of science at the frontier. We're not dealing with a textbook case. We're dealing with an outlier, something that doesn't fit neatly into existing categories, and that means the process of understanding it is going to be messy, contentious, and slow. But that's also what makes it exciting. The anomalies are where the breakthroughs happen. The objects that don't make sense are the ones that teach us something new. 3I Atlas is the third confirmed interstellar object to visit our solar system, and it's forcing a reckoning with what we thought we knew about these cosmic wanderers. The first, Oumuamua, arrived in 2017 and immediately defied categorization. Its elongated shape, somewhere between a cigar and a pancake depending on how you interpreted the light curve, was unlike any asteroid or comet observed before. It showed non-gravitational acceleration, a subtle change in trajectory that couldn't be explained by gravity alone. Some argued it was outgassing, standard cometary behavior. Others pointed out there was no detectable coma, no dust, no gas emissions. The debate continues to this day. The second interstellar visitor, Borisov, showed up in 2019 and was refreshingly normal. It looked like a comet, acted like a comet, had a coma, and a tail, and spectral signatures consistent with water and carbon dioxide ice. It was evidence that some interstellar objects are exactly what we expected: refugees from other star systems ejected during planetary formation, wandering the galaxy until chance brings them close to another star. Borisov was comforting in its predictability. 3I Atlas is neither comforting nor predictable. It has the most extreme behavior of the three. The size, the jets, the composition dominated by carbon dioxide, the statistical improbability of its detection, all of it pushes the boundaries of what we thought interstellar objects could be. If this object genuinely broke apart or behaved in ways that standard comet physics can't explain, it forces us to reconsider our entire framework. Structure and composition become open questions. Maybe interstellar objects aren't just solar system objects from somewhere else. Maybe they're fundamentally different, formed under conditions we don't encounter in our own system. The carbon dioxide-rich composition, confirmed by James Webb observations, suggests formation in a region where carbon dioxide ice dominates over water ice. That means temperatures and pressures in the protoplanetary disk where it formed were different from what we see around our sun. What does that tell us about the diversity of planetary systems? The range of chemical environments where planets and planetesimals form. If 3I Atlas is typical of objects from its home system, then that system looks nothing like ours. The fragility of the object, if it did fragment, raises questions about structural strength. Maybe interstellar objects, exposed to billions of years of cosmic radiation, micrometeorite impacts, thermal cycling in the cold of interstellar space, are fundamentally weaker than solar system comets. They've been sandblasted, irradiated, frozen, and thawed, and frozen again in ways we can barely model. When they finally encounter a star, they don't behave like fresh, pristine comets. They behave like ancient, damaged, compromised structures on the verge of collapse. Our detection surveys are almost certainly biased. We've built models based on solar system comets and asteroids. We assume certain brightness distributions, certain size ranges, certain activity levels. If interstellar objects follow different rules, if they're more fragile, more volatile rich, more prone to outbursts, then our surveys are missing entire populations. 3I Atlas might be the tip of an iceberg, a rare glimpse of a class of objects that's far more common than we realize, but too faint, too fast, or too unusual to trigger our automated detection algorithms. Where did it come from? The trajectory tells us it came from interstellar space, but it doesn't tell us which star, which system, how long it's been wandering. It could have been ejected from its home system billions of years ago, during the chaotic early phases of planetary formation, when gravitational interactions between forming planets fling smaller bodies into the void. It might have wandered the galaxy for the entire lifetime of Earth, crossing spiral arms, passing through molecular clouds, drifting through regions of space we can barely imagine. What would that do to an object? What kind of cosmic weathering occurs over billions of years in the interstellar medium? We don't know because we've never studied it. Alternatively, it could be younger, ejected more recently from a system closer to us. Or it could be a remnant of something destroyed, a fragment of a planetesimal or icy moon shattered by a collision and cast adrift. Each origin scenario implies different properties, different compositions, different behaviors. Without knowing where it came from, we're guessing at its history. The frequency question is critical. If objects like 3I Atlas are common, then either our detection volume is incredibly small, limited by brightness and timing, or we've been extraordinarily unlucky in not finding more. The fact that we found this one, against odds of 1 in 100 million or worse, might suggest that interstellar objects are far more numerous than population models predict. If so, the next generation of surveys will find many more. The Vera C. Rubin Observatory, set to begin full operations in the next few years, will scan the entire southern sky every few nights, generating terabytes of data, detecting millions of moving objects. The statistics will improve dramatically. We'll stop relying on 3 data points and start building real population models. But that assumes we know what we're looking for. Survey biases are insidious. We detect what we're designed to detect. bright objects, slow-moving objects, objects that don't fragment or change brightness unpredictably. If interstellar objects are typically faint, fast, and erratic, our surveys will miss most of them. We need to design detection algorithms that don't assume solar system behavior. We need to expect the unexpected, which is easier said than done when you're processing millions of detections per night. For solar system science, 3i Atlas offers a window into another star's planetary formation environment. The carbon dioxide-dominated composition implies formation outside the typical snowline, in regions where carbon dioxide ice is stable, but water ice might be less abundant. That's rare in our solar system, but could be common elsewhere. It suggests differences in volatile inventories across star systems, which matters for understanding planet formation, atmospheric composition of exoplanets, and the distribution of organic molecules in the galaxy. Astrochemistry depends on knowing what kinds of ices form under what conditions. 3i Atlas is a data point from a system we could never otherwise study. And then there's the wildcard scenario. If 3i Atlas is artificial, if it's engineered, then detecting more such objects opens an entirely new branch of science. Astroarchaeology, the study of artifacts from other civilizations, becomes a field with actual data rather than pure speculation. Every interstellar object becomes a candidate for scrutiny, not just a curiosity, but a potential piece of evidence. That changes the stakes dramatically. Alternatively, if fragmentation is common among interstellar comets, maybe we're seeing remnants of a process that happens regularly as these objects pass through stellar systems. Maybe interstellar comet showers, streams of fragments from a single parent body, are drifting through the galaxy, and we've just encountered one. Next time, we might not find a single object. We might find dozens, all related, all fragments of something larger that broke apart before our surveys existed. The question that keeps astronomers awake at night is this: what if next time we find an interstellar object, we're not prepared for what it brings? What if it's faster, brighter, more active? What if it's headed toward Earth? What if it behaves in ways that make 3i Atlas look tame? We've had 3 interstellar visitors in 8 years. That's a detection rate that's already higher than early models predicted. If the rate increases, if these encounters become routine, we need infrastructure in place, observation plans ready to execute, models that can handle the diversity we're discovering. 3i Atlas might be our warning call, the object that showed us we weren't ready, so we'd better get ready fast. To understand why 3i Atlas is so perplexing, we need to understand the physics of what happens when an icy body approaches the sun. It's a process that's been observed thousands of times with solar system comets, and it follows predictable patterns, except when it doesn't. Comets are primarily ice mixed with rock and dust. As they approach the sun, solar radiation heats the surface. Ice sublimates, transforming directly from solid to gas without passing through a liquid phase. This gas carries dust particles with it, lifting them off the surface and forming the coma, the fuzzy cloud surrounding the nucleus. Solar radiation pressure and the solar wind push this material away from the sun, creating the iconic tail. The closer the comet gets, the more intense the heating, and the more active the comet becomes. It's a straightforward thermal process. Heliocentric distance matters because solar radiation follows an inverse square law. At 1 astronomical unit, Earth's distance from the sun, the solar flux is about 1,360 watts per square meter. At 2 astronomical units, it drops to about 340 watts per square meter. At half an astronomical unit, it quadruples to over 5,000 watts per square meter. Small changes in distance produce large changes in heating, which is why comets become dramatically more active as they approach perihelion. Sublimation energy is the key parameter. For water ice, it takes about 2,800 kilojoules to sublimate 1 kilogram. For carbon dioxide ice, it's lower, around 570 kilojoules per kilogram. That energy has to come from somewhere, primarily solar radiation. The absorbed energy heats the ice, raises it to sublimation temperature, provides the latent heat of sublimation, and accelerates the gas off the surface. The efficiency of this process determines how active a comet can be for a given amount of solar heating. Surface to mass ratio also plays a role. A small comet has more surface area per unit mass than a large one, which means it can sublimate proportionally more material. Thermal inertia describes how quickly an object's temperature responds to changes in heating. Low thermal inertia means rapid response, high activity. High thermal inertia means slow response, delayed activity. These factors combine to produce the activity curves we observe, and they're well calibrated for solar system comets. Sun-grazing comets represent an extreme case. These objects pass within a few solar radii of the sun's surface, experiencing temperatures in the thousands of degrees and solar fluxes millions of times stronger than Earth receives. Most don't survive. They evaporate completely, their material dispersed into the solar wind. A few, like Comet Lovejoy in 2011, have survived perihelion passages inside the sun's corona, emerging battered but intact. But their behavior, while extreme, still fits within the physics we understand. 3I Atlas never approached that close. Its perihelion was around 1.36 astronomical units, according to some orbital estimates, roughly the distance of Mars from the Sun. That's not a sun grazer. That's a respectable distance where solar heating is significant, but not catastrophic. Yet its behavior was more extreme than objects passing 10 times closer to the Sun. That's the paradox. Why might an interstellar body behave differently? Age is one factor. 3I Atlas could be billions of years old, far older than any solar system comet we've studied. Over that time, it's been exposed to cosmic rays, high-energy particles that can alter the chemical structure of ice, creating free radicals, breaking molecular bonds, potentially making the ice more reactive or less stable. It's been hit by interstellar dust particles moving at tens of kilometers per second, each impact delivering kinetic energy that fractures and heats the surface. It's experienced thermal cycling, possibly passing near other stars during its galactic wandering, being heated and cooled repeatedly in ways that stress the structure. Composition is another factor. The carbon dioxide rich composition confirmed by James Webb. Observations suggests formation in a colder, more carbon dioxide-dominated environment than our solar system's comets typically experience. Ultravolatile ices, nitrogen or carbon monoxide frozen at temperatures just a few degrees above absolute zero, could be present in significant quantities. These ices sublimate at much lower temperatures than water. Even at large heliocentric distances, they could drive substantial activity. We rarely see this in solar system comets because they formed in warmer regions where these ultravolatiles weren't retained. But an interstellar object from a different formation environment? It could be carrying ices we never anticipated. Structural integrity becomes critical. Billions of years of cosmic weathering could leave 3I Atlas as little more than a loosely bound rubble pile, fragments held together by weak gravity and thin layers of sintered ice. When solar heating begins, that fragile structure can't withstand the pressure of sublimating gases trapped beneath the surface. The object doesn't break apart because the sun destroyed it. It breaks apart because it was already barely holding together, and the sun provided the final push. Non-gravitational acceleration is where things get really interesting. Some solar system comets show measurable changes in their orbits that can't be explained by gravitational interactions alone. The mechanism is jet thrust. Gas escaping from the surface carries momentum. If the jets are asymmetric, if more gas escapes from one side than the other, the comet experiences a net force, like a tiny rocket engine. Over time, this thrust changes the orbit slightly, typically by a few kilometers in position or a few meters, per second in velocity. It's small, but measurable. Early reports on 3I Atlas hint at unusual acceleration patterns. The data is still being analyzed, the measurements still being refined, but there are suggestions that the object's trajectory isn't following pure gravitational motion. If confirmed, that raises the question of what's driving the acceleration. Is it standard jet thrust from asymmetric sublimation? Or is it something else, something more deliberate? Let's run a back-of-the-envelope calculation. If 3I Atlas is losing mass at roughly 2 million kilograms per second near perihelion, and that mass is being ejected at 0.4 kilometers per second, that's 400 meters per second. Then the momentum per second is mass times velocity. 2 million kilograms times 400 meters per second equals 800 million newton seconds, or 800 million units of momentum per second. Force is the rate of change of momentum, so that's approximately 8 times 10 to the 8th newtons of thrust. Now, the object's estimated mass is around 33 billion tons, or 3.3 times 10 to the 13th kilograms. Force equals mass times acceleration, so acceleration equals force divided by mass. 8 times 10 to the 8th newtons divided by 3.3 times 10 to the 13th kilograms gives roughly 2.4 times 10 to the negative 5th meters per second squared. That's tiny, about 2 millionths of a percent of Earth's surface gravity. But over weeks or months, it adds up. If that acceleration is sustained for, say, 30 days, the velocity change is acceleration times time. 2.4 times 10 to the negative 5th meters per second squared times 30 days, converted to seconds. That's about 2.6 million seconds. Gives roughly 62 meters per second. That's measurable, detectable in precise orbital tracking. It's enough to change the trajectory noticeably, enough to shift the arrival time at closest approach to Earth by hours or even days. But here's the twist. If the ejected mass were traveling at much higher velocities, say 1 kilometer per second or more, you'd need much less mass to generate the same thrust. At 1 kilometer per second, you'd only need 800,000 kilograms per second, less than half the observed mass loss rate. At 10 kilometers per second, you'd need just 80,000 kilograms per second, a fraction of what's observed. Higher exhaust velocities mean more efficient thrust, which is the entire principle behind rocket propulsion. If 3I Atlas were somehow expelling material at much higher velocities than 0.4 kilometers per second, the energy requirements drop dramatically, and the engineered jet hypothesis becomes less absurd. The open question haunting this entire analysis is whether our physics is missing something fundamental, or whether 3I Atlas is simply an extreme outlier. Too big, too fast, too active compared to the population of objects we've studied. Outliers happen. Statistical distributions have tails. But outliers this extreme, where the observed behavior deviates by orders of magnitude from predictions, usually signal that something important is missing from the model. The sun's proximity triggered a dramatic interaction. That much is certain. Whether it destroyed the object, fragmenting it into pieces that will continue to drift apart as they travel through the solar system, or whether it revealed something unexpected, some property or process we didn't anticipate, remains unresolved. The observations continue. Telescopes are still tracking. And in just over a month, on December 19th, we'll get another chance to see what 3I Atlas has become. By then, we might have answers. Or we might have even more questions. While 3I Atlas has been dominating headlines in November 2025, another space science breakthrough has been quietly unfolding that ties directly into the theme of cosmic objects defying our expectations. In August 2025, the James Webb Space Telescope detected something nobody predicted in the atmosphere of an exoplanet designated as L9859b, a mini-Neptune orbiting a red dwarf star about 105 light-years from Earth. The planet itself isn't particularly unusual. It's roughly 4 times Earth's diameter, orbits very close to its star with a period of just 3.7 days, and is tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. These mini-Neptunes, planets larger than Earth but smaller than Neptune, are among the most common types in the galaxy, yet they're entirely absent from our own solar system. We've found thousands of them around other stars, but we've never had one to study up close. So every atmospheric observation is breaking new ground. Webb observed L9859b during transits, moments when the planet passes in front of its star from our perspective. Starlight filters through the planet's atmosphere on its way to us, and molecules in that atmosphere absorb specific wavelengths. By measuring which wavelengths are missing, astronomers can identify the chemical composition. It's a technique that's been used dozens of times now with Webb, and it's revolutionized exoplanet science. The expected result was water vapor, maybe some carbon dioxide, perhaps methane if the planet had a reducing atmosphere. That's what models predicted based on the planet's mass, temperature, and distance from its star. What Webb found instead was sulfur dioxide at concentrations roughly 3 times higher than any theoretical model suggested was possible. The mixing ratio came in at approximately 200 parts per million, an order of magnitude higher than pre-observation predictions. Sulfur dioxide in an atmosphere requires specific conditions. On Earth, it's produced by volcanic activity and industrial processes. It's short-lived in the atmosphere because it reacts with other molecules and gets washed out by rain. To maintain high concentrations, you need a constant source. For L9859b, the leading hypothesis is that intense ultraviolet radiation from the star is driving photochemical reactions, breaking apart hydrogen sulfide or other sulfur-bearing molecules and creating sulfur dioxide. But the efficiency required to produce the observed concentrations is far higher than models predicted. Something about the planet's atmospheric chemistry is fundamentally different from what we expected. The surprise doesn't end there. Webb also detected surprisingly low levels of water vapor. The observations show a water mixing ratio of less than 10 parts per million, far below what formation models suggest the planet should have. Many Neptunes are thought to form beyond the ice line in their protoplanetary disks, where water ice is abundant. They should have accreted large amounts of water during formation. The fact that L9859b appears water-depleted challenges core assumptions about how these planets form and evolve. One possibility is that the planet formed much closer to its star than the ice line, in a region too hot for water ice to exist. That would explain the low water content, but raises the question of how it grew so large. Planets forming in the inner disk typically don't have access to enough solid material to reach mini Neptune sizes. Another possibility is that the planet did form beyond the ice line, but lost its water through some process we don't understand. Extreme atmospheric escape, driven by stellar radiation, could strip away lighter molecules like water, while retaining heavier ones like sulfur dioxide. But the timescales and energy requirements for that level of atmospheric loss are uncertain. There's also the intriguing possibility that the planet's interior composition is unusual. If it formed from building blocks that were sulfur-rich and water-poor, perhaps material from the inner regions of the protoplanetary disk that was transported outward by dynamical processes, then the atmospheric composition would reflect that unusual heritage. This would imply that planet formation is messier and more chaotic than our tidy models assume, with material mixing across the disk in ways that produce chemically diverse populations of planets. The connection to 3I Atlas is more than superficial. Both cases involve objects, one an interstellar visitor, the other an exoplanet, that are breaking our expectations based on what we thought we knew about their behavior and composition. In astronomy and planetary science, anomalies are gold mines. They're not failures of the scientific method. They're opportunities. When observations don't match predictions, it means the models are incomplete, and incomplete models are invitations to discover something new. The L9850 9b results force a reconsideration of many Neptune formation models. If one planet can have such an unexpected atmospheric composition, how many others are similarly surprising? We've characterized the atmospheres of perhaps a few dozen exoplanets out of the thousands we've discovered. If a significant fraction of them turn out to be as weird as L9859b, then our entire framework for understanding planet formation across the galaxy needs revision. The implications for habitability are particularly intriguing. High sulfur dioxide concentrations are toxic to life as we know it, but life as we know it is a narrow category based on one example: Earth. If planets commonly have sulfur-rich atmospheres, and if chemistry in such atmospheres can become complex enough to support self-replicating systems, then the search for biosignatures needs to expand beyond oxygen and methane. We need to consider what life looks like on a planet where sulfur chemistry dominates. We need to think about what metabolic pathways are possible, what waste products such life might produce, and how we detect them from light years away. For volatile inventories across the galaxy, the L9859b observations suggest enormous diversity. Some systems produce water-rich planets. Others produce sulfur-rich planets. The ratios of different elements, the temperatures and pressures during formation, the dynamical history of the system, all of it contributes to a chemical fingerprint that varies from star to star. Understanding that diversity is critical for understanding how common Earth-like conditions are, how frequently the right ingredients for life come together, and where we should focus our search for habitable worlds. The takeaway for viewers is this. In space science today, surprises are the norm. We thought we understood comets until Oumuamua showed up. We thought we understood exoplanet atmospheres until Webb started observing them. Every time we upgrade our instruments, every time we push the sensitivity a little higher or the resolution a little sharper, we find something unexpected. 3I Atlas is part of that pattern. It's the latest in a series of cosmic anomalies, reminding us that the universe is weirder, more diverse, and more complex than our models capture. And that's not a problem. That's the entire point. We're explorers stumbling through a landscape we barely understand, and every stumble teaches us something new. There's one more piece of the puzzle we need to discuss, because understanding 3I Atlas isn't just about physics and chemistry. It's about how we find these objects in the first place, and how we're going to find the next 100 like it. In October 2025, astronomers announced a breakthrough that's reshaping how discoveries happen in modern astronomy. Using machine learning algorithms applied to data from the Zwicky Transient Facility, a robotic telescope in California that scans the entire northern sky every 2 nights, researchers identified a new class of fast-moving objects that had been hiding in plain sight for years. The objects, designated as high-velocity transients, are moving through the solar system at speeds exceeding 50 kilometers per second, far faster than typical asteroids or comets. They're small, faint, and blink past detectors so quickly that traditional detection algorithms flagged them as noise and discarded them. But machine learning, specifically a convolutional neural network trained on simulated fast movers, recognized the pattern. The algorithm sifted through 3 years of archival data, roughly 400 million individual detections, and pulled out 2,347 candidates. After manual verification, 123 were confirmed as real, a new population of objects nobody knew existed. The discovery matters because it demonstrates how much we've been missing. Traditional detection algorithms are designed to find slow-moving objects, things that appear in multiple frames over a night or across several nights, moving predictably against the background stars. Fast movers, objects that cross the field of view in minutes or seconds, don't fit that profile. They trigger the detectors, but the software doesn't know what to do with them, so it ignores them. It took machine learning, trained to recognize unusual patterns rather than expected ones, to see what had been there all along. This connects directly to 3I Atlas and the future of interstellar object discovery. The Atlas survey that found 3I Atlas is an all-sky system, 4 telescopes scanning the entire visible sky every couple of nights, generating terabytes of data. Human eyeballs cannot possibly examine every detection. Software filters the data, deciding what's interesting and what's noise. If the software is optimized for finding typical solar system objects, slow-moving asteroids and comets on predictable orbits, then it's going to miss the unusual ones, the interstellar visitors, the objects with weird trajectories, or unexpected brightening or fragmentation patterns. Machine learning changes the game. Instead of telling the computer what to look for, you show it examples of what you've found before and let it learn the patterns. Then you set it loose on the full dataset and see what else matches those patterns, or more importantly, what doesn't match any known pattern. Anomaly detection, finding the outliers, the data points that don't cluster with anything else, becomes a primary tool, and outliers are exactly what we care about in interstellar object science. The process works like this. You start with labeled training data, images, or light curves or spectra, where you know what you're looking at. You feed that into a neural network, a computational architecture inspired by the structure of brains, with layers of interconnected nodes that adjust their connections based on feedback. The network learns to associate certain features in the data with certain classifications. Fast-moving object versus slow-moving object. Brightening transient versus static star. Asteroid versus comet versus interstellar visitor. Once trained, the network can process new data far faster than humans. It looks at a detection, extracts relevant features, compares those features to what it learned during training, and assigns a probability. This object has a 98% chance of being an asteroid. This one has a 2% chance of being anything we've seen before. That 2% object gets flagged for human review. Astronomers examine it, decide if it's interesting, and follow up with additional observations if warranted. The successes so far are impressive. Machine learning has identified rare variable stars, discovered new types of supernovae, classified galaxies at scales impossible for human researchers, and now found entire populations of fast-moving solar system objects. The Zwicky Transient Facility results are just the latest example, and as data volumes explode, the importance of these tools only increases. The Vera C. Rubin Observatory, currently in final construction and testing in Chile, is about to change everything. When it becomes fully operational, expected within the next year or two, it will image the entire southern sky every few nights using a camera with 3.2 billion pixels. Each night will generate roughly 15 terabytes of data. Each year will produce a catalog of tens of billions of astronomical sources and millions of detected moving objects. Human astronomers cannot possibly review that volume of information. Machine learning isn't optional. It's essential. For interstellar object discovery, this means the detection rate is about to skyrocket. We've found 3 interstellar visitors in 8 years using surveys with limited sky coverage and relatively simple detection algorithms. Rubin will have full hemisphere coverage, unprecedented sensitivity, and machine learning algorithms specifically trained to find anomalies. We might start finding 1 interstellar object per year, or 1 per month, or even more. The statistics will go from embarrassingly sparse to overwhelmingly rich. And with statistics come the ability to test hypotheses, measure population properties, and understand whether 3I Atlas is an outlier or the first hint of a common phenomenon. But machine learning has limitations. Neural networks are only as good as their training data. If you train on solar system objects, the network learns to recognize solar system objects, and it might miss something truly alien that doesn't fit any category in the training set. Adversarial examples, data intentionally crafted to fool neural networks, are a known problem in machine learning. The universe isn't adversarial, but it is creative, and it might produce objects so different from anything we've seen that even our best algorithms fail to recognize them. There's also the black box problem. Neural networks make predictions, but they don't always explain why. A network might flag an object as unusual, but when you ask it to explain what features triggered the classification, the answer is often opaque. The decision emerged from thousands of weighted connections across multiple layers, and there's no simple narrative to extract. That's fine for initial flagging, but it means humans still need to be in the loop, interpreting results, deciding what's worth following up, and maintaining the scientific rigor that separates discovery from artifact. The broader lesson is that space science is no longer just about pointing telescopes at the sky and taking pictures. It's big data, distributed computing, machine learning, real-time theory testing. The process of discovery is becoming industrialized, automated, scaled up in ways that would have been unimaginable 20 years ago. And that's necessary because the universe is bigger, more complex, and more surprising than we ever anticipated. 3I Atlas is a preview of that future. A strange object caught by an automated survey, flagged by software designed to find the unusual, followed up by multiple telescopes and instruments, analyzed using models that draw on physics, chemistry, and statistical inference. The discovery pipeline worked, but just barely. We almost missed it. If the timing had been slightly different, if the sky had been cloudy, if the survey hadn't been looking in the right direction at the right time, 3I Atlas would have passed through the solar system unnoticed. We got lucky. Next time, we need to be better than lucky. We need infrastructure that can handle the flood of data coming from next-generation surveys. We need algorithms that can recognize the truly weird objects, not just the ones that look like solar system comets. We need follow-up capacity, enough telescopes with enough time to characterize every interesting detection before it disappears back into the darkness of space. And we need frameworks for interpreting what we find, models flexible enough to accommodate objects that don't fit existing categories, and scientists willing to seriously consider hypotheses, even speculative ones, when the data demands it. 3i Atlas is teaching us that the cosmos is full of objects we're not prepared for. The jets that shouldn't exist, the energy budgets that don't close, the statistical improbabilities that keep piling up. These aren't failures. They're invitations. The universe is showing us the edges of our knowledge, the places where our models break down, and it's asking if we're ready to step beyond them. Because the next interstellar visitor could arrive tomorrow. Or it could already be here, lurking in archival data, waiting for the right algorithm to notice. And when we find it, when we realize what we're looking at, the questions it raises might make 3i Atlas look like a warm-up act. Are we ready for that? Are we ready to discover something we don't understand? Something that challenges not just our models, but our assumptions about what's possible in the universe? 3i Atlas is the warning. The real test is still coming.